We're recording. Is this thing running? Really? Beep, 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 beep.
Morning.
Good morning, guys. How you doing? I guess you said that already, didn't you?
Yep.
All right. So today, guys, we're going to be talking about the dual nature of light. So it turns out that Mr. Newton here comes up with a particle theory of light, and he figures that if light is a particle, that light is going to travel faster through more dense materials.
Okay, so he's hypothesizing that light actually is pieces.
Yeah,
little
it's
particles.
pieces of light, and that the pieces of light, if light is actually made of pieces, then light travels faster through more dense materials.
Okay.
All right, so it's going to go faster. And then we got this guy Huggins, who doesn't quite understand the gravity of the situation. Comes up with a wave theory of light. All right. And Huggins says that light travels slower through more dense materials.
All right, so we've got the party split in two.
Mm-hmm.
Okay.
Dueling scientists. The problem is that when these guys were doing their work and thinking about what light is, there was no experiment available, and there wasn't enough equipment available to find out what the speed of light was.
So these guys just made these hypotheses without any lab data to back them up?
Yeah.
They get their name in the books?
Exactly. Well, they were just hypothesizing about what light was. You know, they were doing what scientists do. They were making hypotheses.
All right, so it looks like Newton won?
Newton won, you know, because
I thought they thought light was just...
Because he understood the gravity of the situation.
Oh.
Yeah, because he was famous for other reasons, obviously. His theory was actually favored.
And it was favored for about 100 years. Then, after that, they had some experiments that suggested that light was more of a wave, although they still saw it as a particle. So it spent another 150 years that way, with both theories being prominent, which is why we call it the dual nature of light.
All right, so in 1850,
all right,
the idea of light changes.
That's a long time after Newton.
It is a long time. Like I said, about 250 years after Newton and Huggins. The first experiments were done. They found the speed of lights. How they found the speed of lights isn't really part of this class. It's more of a physics idea. But they did find that light travels slower when you put it in more dense substances.
Okay.
Okay. And so now light is considered a wave, not a particle.
Okay, so pure energy.
Mm-hmm.
So they kind of went back and forth, back and forth.
And this is what we mean about the wave-particle duality, or the dual nature of light, is that you get this idea that light can be a wave or light can be a particle,
all right,
depending on what experiment you're doing at the time.
50 years later, Max Planck.
Yeah, 50 years later.
Energy can be either released or absorbed by atoms only in discrete packets of some minimum size. So in other words, energy is chunks.
Right, so it's quantized energy.
Yep, quantized energy, little chunks of energy, not a continuous stream of.
And that makes sense because the word quantum means a fixed amount.
When I hear the word quantum, I think quantity.
Right,
a quantity of energy.
And
all right.
It's a quantity of energy. So he comes... And a quantum is the smallest unit of energy that can be emitted or absorbed as electromagnetic radiation.
All right, so the least amount to get those colors and those wavelengths.
Right, exactly, and we haven't even seen those colors yet.
Yeah.
But every atom gives off a different bit of light.
Okay.
Okay, different colors of light.
Right. Ooh, there's a computation that accompanies Planck.
Planck. So Max Planck found an equation that he used to determine the energy found in electromagnetic radiation. So he actually calculates the energy of the light or the electromagnetic radiation that's coming out. Yeah. And his equation is E equals h nu.
Okay, so energy is related to frequency.
Right. Energy is directly related to frequency and this value h.
Okay.
Okay. And the E is a measure of a quantum. E has to come in certain sizes.
Okay, a certain amount of energy. All right.
And that's guided by what h is. Okay, multiples of h. So E is energy, measured in joules or kilojoules per mole, depending on what you want to measure.
Yeah.
Okay, whether you want to measure small amounts of energy or large. Planck's constant comes in two versions. One that measures in joule seconds and one that measures kilojoules per mole.
Okay.
So the first one is for measuring a single photon
of energy, yeah.
And then the second one is for a mole of photons.
Right.
So if you want 6.02 times 10 to the 23rd photons. And that's kind of useful because you don't often get photons coming by themselves, one at a time.
So a single photon of light has a particular energy based on Planck's equation, and a mole of photon of light is just a little conversion.
Right.
Okay.
All right, and then nu, we already know.
Yep.
Its frequency
That was the last
measured
video.
in hertz.
So the amount of energy is equal to frequency. Okay.
All right, what Planck proposes is that an atom can absorb a quantum of energy, so a certain amount, a multiple of that h,
Okay.
by factors of h nu, which
All
is
right.
a factor of h, right? If an atom emits energy, it does so also in factors of h nu. So an atom can only absorb a specific amount of energy, a multiple of h, and it can only emit a multiple of h.
Huh? All right. In English, in other words, you can calculate the amount of energy absorbed by an atom,
By taking h nu.
and you can calculate the amount of energy released by an atom.
Right, by taking
Okay.
h nu.
Okay.
Yeah. In English.
Got it.
All right. All right. And that's what hopefully I said right here. Energy always
Yeah.
comes in multiples
using-
of h nu.
You're using algebra terms.
Sorry. All right, now the fun part was no experiment was produced to prove this.
Again, they're taking this guy's word for it without experimentation.
Hey, it was the best hypothesis of the time. It wasn't
Okay.
quite a theory yet. All right. So along comes
Albert Einstein.
some guy named Al. All right. So Al came around in 1905, and he's German.
They were all basically physicists. Nobody was a chemist. They were all physicists.
No, they were all physicists. They were mostly studying the
Yeah.
physical nature of the world. But by studying the physical nature of the world, they actually kind of made a fuzzy line between physics and chemistry, because this has to do with how atoms are set up, but also how the physical world works. So he did something called the photoelectric effect.
All right.
And he found that by shining light on a surface of a metal, you can cause it to emit electrons.
Okay, so you can knock the electrons off a piece of metal, basically.
And each metal has its own minimum frequency of light for this to occur. So you've got to hit it with a certain frequency of light.
So copper versus aluminum, you can knock off copper electrons and you can knock off aluminum electrons, but it's not necessarily going to be the same frequency of light.
Right.
Okay.
Yeah. They'll require different frequencies.
All right.
Okay. And like we knew from before, different frequencies means different amounts of energy. Okay. So Einstein assumed that this energy striking the metal must be a stream of tiny packets, and he decided that this tiny packet of energy was a particle called a photon.
Okay, so he coins the he coins the term photons.
Yeah, he starts using the word photons here. And basically, he decides that light is made of particles.
So he figures that since he's knocking off electrons off a piece of metal, he figures that light isn't just pure energy. Something's knocking those electrons off.
Right.
And it must be little particles of something knocking off those electrons.
Right, because those electrons are actual matter. In order to move matter, you need to move matter by hitting them with something.
Yeah.
You can't just shine light on them.
Yeah.
So here's the idea. This is our piece of potassium here. Okay. When he shines red light on it, red light has a low amount of energy.
Nothing happens.
As you remember from last time. Right? Nothing happens. No electrons get liberated. Green light has more energy than red. So we shine a green light on this piece of potassium and we can knock off an electron.
And it has a velocity.
And you can calculate what the velocity of that electron is, and you get 2.96 times 10 to the 5th meter per second. That's pretty fast.
Yep.
Okay. Now, blue light, even more energy. You hit this piece of potassium with a blue light, and you get an electron that flies off even faster.
Yeah.
So what Einstein has proven with the photoelectric effect is that that different wavelengths of light have different energy.
So it's green is technically the minimum amount of energy that can knock an electron out of potassium metal.
In this example, yes,
And
that's
anything
true.
above green light is going to knock it out and give it more speed.
Green, blue, indigo,
Yep.
violet, ultraviolet.
You imagine what
Gamma.
violet can do if blue can do that velocity?
It'd be pretty fast stuff. All right, so what does this mean that the photoelectric effect works? Well, Planck's equation can be used to calculate what the energy is of the light that's coming off of All right, so an example of
Planck's calculation.
Mm-hmm.
All right, let's see. Calculate the energy of a single photon of light with a wavelength of 589 nanometers. So this is going to take 2 steps.
Okay, so first I got to take my 589 nanometers.
And find frequency, right?
And find frequency.
So it's C.
So C equals...
and you'd want 3 times 10 to the 17th, correct?
Right, because it's in nanometers. So 3.00 times 10 to the 17th nanometers. So we're going to divide both sides by 589.
Yep.
Divide by 589 nanometers. So nanometers cancels. I wind up with a unit of hertz.
That would be 5.09 times 10 to the 14th. So there's the frequency of that wavelength.
Okay.
Right.
So
step 2 now, right?
Step
would be Planck.
2, we can use E equals h nu.
All right, now since they only want 1 photon of light, we can use the 6.62 times 10 to the negative 34, right? Because that was joule seconds.
That sounds right?
Yeah, so 6.626 times 10 to the negative 34. Is that right?
If you say so. Joules seconds. So let's see. Joule seconds is there because we want hertz to cancel with seconds. We'll be left with joules.
All right, so we've got 5.09 times 10 to the 14th times. All right, so the answer is
3 sig figs.
3.37 times 10 to the negative 19.
That's not a lot of energy, is it? Negative 19 is a small amount of energy.
Yeah, really.
But I guess we only have 1 photon of light here.
Yeah, that's true. So for 1 single photon.
Ooh.
So this is
electrifying.
Yeah, oh gosh. I was thinking it was more like the photoelectric effect, but electrifying is also the same thing.
Photoelectric effect.
Let's see. Copper is bombarded with high energy electrons. X-rays are emitted. Okay.
Is that how they make X-rays at the hospital?
I don't know.
Huh.
Maybe. It's pretty high up there on the electromagnetic radiation. Calculate the energy in joules. So it's asking for a specific unit.
Right.
Associated with the photons if the wavelength of the X-rays is 0.154 nanometers. Look how little that is.
Hey, those are small. X-rays are tiny.
Pretty small. So we're going to have to do 2 steps again, right?
This looks like 2 steps again.
When they give us wavelength, we've got to get frequency because frequency is the unit in Planck. All right, so 2-stepper.
So we'll set up our problem. Divide both sides by 0.154 nanometers. And nanometers cancel, leaving us with per second, which is hertz. 3 sig figs here, Miss G.
1.95 times 10 to the 18th per second.
Okay, so hertz. So 1.95 times 10 to the 18th hertz. Then we got to take this problem a little step further. Energy is equal to h nu.
Well, we want it in joules, so I'm sticking with the 6.626. Yeah?
6.626 times 10 to the negative 34th times 1.95 times 10 to the 18th hertz. That was joules seconds.
1.29 times 10 to the negative 15th joules. And that's a single photon.
And that's a single photon, and that's what they asked us for, joules.
Correct.
So each photon has 1.29 times 10 to the negative 15 joules. That's actually more energy than that other light that we had in the last problem, isn't it? Because the last problem was like negative 19th joules.
Yep.